Okay, here we've got another experiment with Muscaluk here. Well, not with me, but with all these chemical stuff. I'll be doing the experiment. Now, this is about light path, and it's the first of a number of experiments that deal with colorimetry. And the real thing about colorimetry is it's all about light being absorbed and going through solutions, and some of those photons being absorbed. And so you've got to have a solution that will absorb some type of electromagnetic radiation. And here I've got a sort of a classic, my morning coffee that I brewed up. And here we are. I end up using my Chemex to take 20 grams of coffee and dilute it with 250 mLs of 204-degree boiling water and filter it through. Now, this is the solution that I get. It's a nice strong cup of coffee. I only have one cup, so I enjoy having a very good cup. Now, what I've done is I've taken the same amount of coffee. In this case, there's about 50 mLs of coffee, about a fifth of a cup, and I put 50 mLs of the same coffee here, the same concentration, but then I diluted the solution up to about 160 mLs. So I've taken the original solution, changed it from 50 to 160, so that's about 3 times the volume. So this coffee is 1/3 as concentrated. And here you can see, definitely, when you look through it, it looks lighter because it's not as originally concentrated. But this is what this part of the experiment is going to all be about. I'm going to take the camera and we're going to go and look at the same solutions from above. And this is sort of the interesting part. Let me get that lens going through here. When you look from above, both solutions look identical in terms of concentration because they have really the same amount of coffee in them. I'm looking through all of the coffee in both cases, but here, let me get the camera back again. When I look through the side, the more dilute solution has a lighter coloration to it. So this is like part one of what we're going to do in terms of colorimetry, which is a really, really important diagnostic tool. You'd be surprised how many applications are involved with it. Well, we're going to take this coffee and put it back here. It's cold now anyway. And I'm going to make up a solution, in this case using a blue dye from my McCormick color set. So 7 drops of my concentrated food coloring. And here we go. 1, beautiful, 2, 3, 4, 5, 6, 7. Now, the amount of drops isn't all that critical. What really is critical is we want to get ourselves a very, very dark solution. I use this glass stir rod, and I'm going to stir it up. And right now, it's almost so concentrated that you really can't see much through it. There's very little transmittance of light going through this solution, and we'll talk about the type of light that's being absorbed in the next experiment. And that's pretty much what I want. I want a relatively dark solution because I'm going to dilute it. I'm going to take 20 mLs of it, and that's where I've got my solution here for. I'm going to get about 20 mLs. I've got a 10 ml graduate, and, well, yeah, I think I got it right on the money there. 10 ml, certainly within 1/10 of an ml of my solution there. 10, and now I'm going to get it up to about 20. And then I'm going to add 10 mLs of water to this. I'll get my water out and take that 20 mLs and, oops, here we go, and dilute it with 10 mLs of water. Whoops, not quite, a little bit too much. and any of the 10 mLs that were trapped there in the graduate cylinder are now going to be in this water. So this will take all the 10 mLs I measured out, even the drops that were left behind, and get them back into my solution A here. Now I'm going to do this so I have 30 mLs of my solution A. I'm going to get 20 mLs of water added to this, so I'll have 40 mLs of solution, and I'll just keep going across. So let me do that now, and we'll time lapse through it. So here we go. Next step. We're back, and I've got my solutions. I've got my stock solution, which I've got here, that I made from my concentrate day, and you saw the fast forward as I did my solutions A, B, C, and D at various concentrations. And the next step is to compare these solutions in terms of path length, to do in effect what I did with the coffee. So what I did is I put together and have one of these little cuvettes. These are standard cuvettes that are used in colorimeters. They're all supposed to be identical in terms of transparency. And I put in about 1 centimeter in terms of depth of my stock solution, my 10 micromolar. And I've got a my little iPad here of sorts. In this case, it's a Galaxy. And what I then did was to try and look at both of these at the same time. So I've got my empty cuvette here, and my cuvette there we go, saved it. Oh boy, don't have to curse too much on that one. Now, it's with my 1 centimeter there, and I'm going to hold them next to one another, wrap my hand around them, and I'm going to take my dilute solution here, D, and this is going to be the extreme, and I'm going to add D, my diluted solution, into the cuvette that's right next to it. And I'm going to keep dropping it in. When I look at the two, I see my D is a lot clearer, a lot lighter than the original. Let me see if we can see this on your camera. Here's my camera. Yeah, you can see the one to the left is the stock. The one to the right is our D, which is significantly more dilute, and it is lighter. They're not the same color as we look through them in terms of brightness. But I'm going to change that. I'm going to, whoops, let me get back to my Chrome here and get a white background. Okay, I've got a white background here. I'll use that. And try not to tip anything over, and add more of D. So I'm looking through more of D, and here I'm adding more of it, and it's looking a little bit darker, a little bit darker, a little bit darker. Still not quite as the equivalent of my 1 centimeter. It's getting close now. Not quite yet. A little bit more. Just a touch more. Now I'm going to look from above and try and compare the two in terms of their darkness. And to me, it's looking like I could use just a little bit more D to make them identical in coloration. And this is a judgment call. Now you can use some digital devices to do that, but I think the two solutions, when I look through them, look pretty much the same. So, I'll hold this up to the camera. And now, let's see. This is a little bit harder for you to see, but looking through there without spilling it, the two solutions look like they're pretty equivalent, but here they are. In terms of, here, let me put this against a white background. There you can see, there. So I've got the height set up to compensate for the concentration. Now I've done that with all 4 solutions. And let me show you the results that I end up having. And here we go. I've got this set up there. Let's see, can we see that pretty well? And here's my solution A with about 1 centimeter of height that I made up at 10 micromolar. And then I've got my solution B, which is about 6.7 micromolar. And I've got my, assuming A, I have my stock, then A, now B, which is about 5 molar, half the concentration, and significantly lighter. And then I've got C, which has a concentration of about 4 micromolar. And then here is finally my D, now they all, as you can see, look quite different in terms of when you look at them from the side, but from the top they're almost identical. In fact, what I did is I took a picture in the dark with just the bottom lighting, and I'll post that up after this, and we'll have the data, and we'll see what light path has to do with concentration and the colors that we see in colorimetry. Okay, that's it. We'll go with the data next. Okay, we've done our experiment, and here I've got a picture of the 5 solutions that we made and the cuvettes that I put them in and the height that we had. So remember, we had our original 10 micromolar blue dye solution, and I took that solution and held it up against some light, and then filled the second cuvette, looking down through it, through the barrel, and kept adding solution until the colors were pretty much the same. And here's my final picture of both the stock and A, B, C, D, all looking through against a white background. As you can see, they look pretty close together. Again, this is judging by eye, but still, I'm pretty happy with that. Now, let's graph this and see how it runs out so we can interpret the data. Now, here I've got the concentration, and I can put in the height. And I'm going to put in 1.3 centimeter, which was the height of our stock solution that we presumed was 10 micromolar. Now, what I'm plotting is not the 10 and the 1.3, but I'm plotting the inverse of it. You're going to see 1 over centimeter. I did that because I wanted a relationship that's a direct one, because the actual relationship is an inverse, where the more dilute the solution, the lower the value of the concentration of the solution, the higher this thing had to be. So I'm plotting the inverse because it's inverse relationship, at least I think so. We'll put in the data and see. So you can see I've got the calculations here. Now, right now, the 6.7 molar solution has the Excel value divided by 0, which it doesn't like because I've got 0 for our height. But let's put in the actual 1.9 centimeters. And that'll plot nicely. Love Excel. I mean, having this stuff done and not having to do it on paper is just beautiful. It's worth learning how to use Excel just for this graphing feature. Okay, there we go, 2.2. We've got 3 points, but let's add 5 and get my 2.8 centimeters, which was required to get that same coloration. And now, finally, I'll put in that last value, which was the 3.3 centimeters. And voila, there we get our points. And I've got a best fit curve that's automatically plotted in here. And I've got it, so it gives me the graph equation, the y equals mx plus b. And here I've got my r square, our relationship. The closer this is to 1, the better our data. And having a 0.99 when you've only got 2 significant digits for this, and also doing this by eye, I'm real happy with this experiment. This classic method of finding concentrations, like, if I had a solution and didn't know its concentration, I would end up doing this experiment with it. And if I knew the height, let's say I knew the height was 2.0, I could figure out what the concentration of that solution was just by looking at it, not having to do any chemical stuff or filters or anything else, and actually get it down to the micromolar. This type of analysis, this colorimeter, has been around for quite a while. In fact, let me pull up a web page. And this is in a scientific museum instrument. And here's a version of this early calorimeter, which is right here, where you'd end up having different heights. They have some glass tubes here, and you'd adjust these heights into solutions, and you could very quickly find the concentration of a solution. And this was this is a 1941 version, but these were developed back in 1870. Now here it is. It's a Dubosq. Let's see how that's pronounced. Here we go. Jules. Let's pronounce his name correctly.
Jules Dubosq.
Dubosq. Okay, it's a Dubosq colorimeter, and the modern versions of it are pretty much the same thing, except you have a digital eye, which is pretty easy to do right now. They've got where you put your solution in, and then they've got a glass blank, a standard that you can do some comparison at. And here, a bargain price, $5,900. And here we were able to do an experiment that, worked out pretty well with this, maybe about, my guess is about maybe 50 cents worth of cuvettes. What a deal. Okay, there's our experiment.